engineers. My name is Rachel deBrabander. I am a freshman engineering student at the University of Maryland, of course. I am a civil engineering major with the intent of focusing on the environmental and water resource track. I'm from St. Mary's County, Maryland, and for this project I am analyzing this plastic folding table. So of course it's a plastic folding table. It is intended to be able to put things on, and the folding legs make it easy to transport and to store. The reason that I decided to pick this table was in part because it's been my desk for this online semester in quarantine, so we've gotten a really tight bond here going on, and then also because my initial reaction when we got the project and we could analyze any structure we wanted was to really, go big or go home. I was looking Golden Gate Bridge, I was thinking Eiffel Tower. But when I kind of stepped back and reflected, I realized that I think it's important to recognize how so many structures just in everyday life, simple things, are feats of engineering. So I wanted to look at something that seems kind of mundane and look at it from an engineering perspective. So the first set of calculations that I did was free body diagram and structural supports. So I looked at the legs and analyzed them as rollers since they can only move in one direction. I decided to look at the loading of the table in a couple different scenarios. I looked at the table empty, I looked at the table with different weights of force on top of it representing different objects, and I used my equations of equilibrium to find just some different weights and how much the rollers would be supporting depending on the loading of the table. The next thing that I looked at was the 2D rigid body equilibrium. So as Dr. Young has told us in class, sometimes these projects are a little outside of our wheelhouse of skills, so sometimes we need to, simplify it, nullify some things, and look at it with what we know, and I decided to look at the 2D rigid body because that's something that I'm comfortable with, and it's a different angle to look at the table. So I looked at it. I decided to look at the legs and the angled supports as force vectors, and I had a uniformly distributed load on top with an unknown value of W and solved for the max W in that situation before it would exceed a certain weight. So again, I just thought it was an interesting way to look at how the table would fail under certain circumstances. My third category was centroids and moments of inertia. So in a lot of my analyses and calculations, I assumed that the structure was symmetric, and I tried to load my table symmetrically. So I think that knowing where the centroid is obviously very important to make sure that you're loading your table symmetrically, and just, in general, you never know. You got a party or something, you might want your hors d'oeuvres to be nice and centered. It's important information. The final category that I looked at was buckling, which I think was the most interesting and also the most challenging. It was one of the first ones that I started looking at, and I looked online, and the specifications for the table said that the max weight should be around 300 pounds, and I considered, with safety factor and everything, it definitely shouldn't be exceeding like 1,000. And I'm doing my math out, and I'm getting 300,000 pounds, I'm getting 70,000 pounds, and I was like, something is not adding up because this table is not holding several cars. That's just not what's going on here. But I decided to step back, and I tried to think about the type of problems that we did in class and what aspects of the structure I was analyzing. And I realized that the reason my numbers were coming out so wacky was because I'm not looking at the table if I was looking at the buckling in the legs, because all that this leg is a steel rod, and a really high force is sensible to cause failure in just a steel rod, not the table. So when I went back and tried to do my calculations again, I assumed that the plastic tabletop was rigid and wouldn't deform, and only looked at the buckling in the legs and the structural supports. And when I used my equations and did all the math out, I found that the angled supports fail before the legs, which I think makes sense because the legs are the primary support of the table and the angled members are a secondary, supplementary strengthening structure. So it makes sense that the secondary structure would fail before the primary support. That's my project. That's me and my table. Thank you, Dr. Young, for this great semester, and live long and prosper.